Hi, I am from Social Research Insights. Today in this video cast I am going to explain you how to do regression analysis. In fact, this is the part number 2 of my previous video on regression analysis. The mission of the Social Research Insights is to promote the open source software for data analysis for both academic and corporate research needs. Regression analysis is very much important for social research. Where we can do the regression analysis as bivariate analysis and multivariate analysis. In this video cast, I'm going to explain you how to interpret the regression results and how to do a statistical test for error. In my previous video, I explained what is the simple linear regression and how to test the significance of the regression coefficients known as beta naught, beta 1 and E hat. This is for the population, and for sample we perhaps have to write the regression equation in a different way. I'm going to show you how the expression for the simple linear regression for the sample. For sample we have to say y I is equal to a plus x b, or I can write it as b x, where in sample a is actually equal to beta naught and b is actually equal to beta 1. In population we call a as beta naught and b as beta 1, and E hat is actually the error for the population, but in sample we call with other name called residual. So in sample the deviation of the variable data from its center, which means mean, is regarded as R. Precisely, I can write it as R is equal to let's say, for example, if I'm finding the error for variable y, which is a dependent variable in this case, yi minus y bar. So this is regarded as the residual. The residual in the sample for the data under study. So here the data variables are x and y. Y is a dependent variable and x is independent variable. A is intercept and B is slope. This is how we have to perform the regression analysis when we have this sampling data or data from the sample, some sort of sampling procedure. And as usually we'll try to find the A and B, but in LibreOffice Calc we have a wonderful function known as Linus, which is a short form for the linear estimation. So I'm going to use this Linus function to compute the constants and the only constants, I mean the intercept and the slope, but I have a different procedure to compute the error. We also call it as residual in sample, but in this video cast, which is part 2 of my series of presentations on regression analysis, I'm just going to explain you how to test the residual. In my previous video, I explained how to test the significance of the coefficients, and in this video, I'm going to explain the statistical test for the significance of residual. So the idea of significance arises when we have the sample data and when we compute some sample estimates, we actually don't know whether the same the size or the effect can be observed in the population or not. So for example, if I have a sample with some certain data points, a sample of x or y with some data with certain data points y1 comma y2 comma y3 comma, and we can compute the a alpha, b beta, or beta naught and beta 1, anything, whatever it may be. Sorry, a and B. Actually this is only sample information, so whatever we compute from the sample, it is only sample information, but we don't know exactly in case if we treat these as effects that we computed from the sample, we don't know the same effect lies in the population or not, so whereby we might require some statistical test in order to assess if the difference between the population parameter and the sample statistic is actually significant or not. For example, as I said, in population we call it as beta naught and beta 1, and in sample we call it we refer the coefficients as a comma b. Suppose if we compute a comma b, it is only the sample information which is computed from our data, sample data, but we don't know whether the same effect a can be observed as it is in the population or not. So in order to know whether the same effect can be observed in the population or a different effect will be can be found instead of the effect that we are observing from the sample, we got to do some statistical test with a null hypothesis that the difference is not significant and and with the alternative hypothesis that the actual information that we gather from the sample is significantly different from the population the same information of the population. So this is what is the idea of the significant test. So in regression, as I already told you, if we compare the beta naught with the standard error of beta naught, then we'll get a t statistic, and with the same procedure we can also find the t statistic if we divide the beta 1 with the standard error. So this is actually the concept. I only explained in my previous video how to compute the how to assess this statistical significance of the slope and intercept, but I did not explain how to assess the significance for error. Error. For error, as I said, in sample we treat the error as residual, which is the difference between the individual data point to that to its center, which means average. So we will be having some information from the sample, and we have to test if the same information can be observed from the population. For that, we have a beautiful statistical test for residuals, that is chi-square test. I mean, we need to use chi-square test since it is error. For all the deviation, any measure of the deviation can be studied with the help of the chi-square test. The formula goes in this way, that if we sum up all the error terms, I mean the points, let's say for example, after computing the error is actually a variable, so we'll be having E1, E2, E3. This is population, okay, it's not the sample. In sample we'll be having R1, R2, R3. So this is the error term or error variable, so till En, and we can actually sum up all these the error the values, and we can take the sum here, that is sigma for all I E I. So this is hat, because this is estimation. We are going to estimate it. It's not actual error. When I say E, it is actually population information, but when I put the hat, it is actually sample information. It is only the estimate of the error. So now when I divide it with the variance of the error, then actually I may be computing a chi-square statistic. That is, the chi-square statistic roughly equal to 1 by sigma square sigma for all I E I hat square. So the sum of the error values, squared error values, when divided by the variance, that will become equal to the chi-square distribution, and we can find the inverse value of the chi-square distribution with the help of n minus 1 degrees of freedom, and at some alpha, then we can compare it with the calculated chi-square value, and finally we can take the inference. If the calculated chi-square value is less than the critical value, then we will be accepting the null hypothesis that the actual the sum of the squared errors, SSE, sum of the squared errors in the population is equal to 0. So whatever we may be calculating through the sample data, regardless of the sample data, the actual squared sum of error, sum of the squared error in the population is actually 0, despite of the value that we find from the sample. So this is the plot for the significant test for the error variable. Okay, so I'm going to show you how to do that in LibreOffice Calc. We already have some information, sample data here, and I computed the beta naught, and I mean the beta naught hat and beta 1 hat for this data, and I can compute the fitted values first. For the in order to compute the error, we first need the fitted values, or fit values, whatever it may be, fit values. And the fit value is none other than let's say, for example, if the simple linear regression equation is y hat is equal to alpha plus beta x, then the x plus r hat or e hat. So I can say, so I can also write it as beta naught in our old fashion, and beta 1, but I have to put hats for the sample. So I can do this. This is actually the fit value. Y hat is a fit value, and now the actual instead of the fit value, I can take I'm sorry, let us assume that this is an actual value. The actual value minus beta naught minus beta 1 x is going to be error. So my error, we can find the error by subtracting both beta naught plus beta 1 x. So we just have to take the part of the right side expression to the left, and then we'll get the error. So as such, it is not going to be actual error, but we have to make a small correction. I'm going to show you that in LibreOffice Calc. So fit value is going to be, as I said, the fit value, as I said, is going to be we have to subtract the beta naught together with beta 1 x. So we are going to do that in, so beta naught, where is beta naught? This is the beta naught. Let's say I think I have to take y minus take the bracket, and beta naught multiplied beta naught plus, because we have to take the plus, isn't it, when I put the bracket, plus beta 1 multiplied x. So our error is ready. So it is not actually the error, so there may be a different I mean, it is a slightly different from the actual residual. Sorry, this is actually the fitted value, and from the fitted value we have to compute the error. Okay, this is the fitted value, fit value. Sorry, this is error actually. The fit value will be different. Fit value will be, the fit value yi is equal to beta naught plus beta x plus e. So we don't know e, so first we are going to compute the fit value without e, and after that we subtract this value from the actual value in order to get the error. So that is actually the plot. So this is not the fit value, this is actually the error value. So for fit value we have to beta naught plus beta 1 multiplied x. So that is our fit value. This is our fit value. So actually the right value is not 0.9. The straight line, the actual value is 0.9, but on the straight line, the fit line, the line of fit, we are going to get only 0.3, 0.32, but we do not get 0.9. So whatever is the remnant will going to be the residual. So in this case, let me say, for example, if you have some, let's say we have some regression, the actual line, trend line, we are going to have the regression line passing through this data points, and now let's say the actual value is 0.9 here. Here it is 0.9, 0.9, but the fit value, this is the fit line of fit, a regression line. This is a regression line. So actual value on the regression line is going to be 0.3. It is actual value is 0.9, but the fit value, which means the value that falls on the regression line, is going to be 0.3. It is only 0.3, so approximately we have 0.6. 0.6 is the residual, so there's a huge the error. So now the error, this is not actual error. Error is going to be the actual value minus the fit value. So that should be the error. So it is roughly 0.6 if you observe. And let's see that what's going to, what happened here? Oh my god, it's actually, this is they are constant. B23 is actually, I have to put a dollar string before the alphabet, and because they are not going to change, isn't it? Only the B2 value is going to change, so that is why there is a problem. So now it is okay. So copy, and here we don't have a problem. So now if I add these two values, that should be equal to 0.9. Let's see, is it going to be the actual value from the regression? This is from the regression. So it's equal to the error plus the fitted value. Sorry, plus the fit value. So 0.64, it is not actually the actual value. We still have some error to be that we need to add to the error. So now let me, so our regression is not perfect because we have gone for the simple linear regression, but the case might be a quadratic regression, maybe the polynomial regression. So we don't know. So the regression line is not able to explain the relationship between y comma x. So that is actually the error. So let us this 0.64, 0.9 minus the actual value minus the error, that is the remnant of we still have the error left with, and the total error is going to be the final error. I call the final error, and this is going to be the error, the plus the actual error that we so it is still not equal to 0.9. So is equal to the error plus the fit value. It's not going to be, I'm sorry, I did a mistake. I think here it should be the error, isn't it? We thought about the fit value plus error is going to be the actual value. So 0.9 should be the actual value. Oh, in this case the error is exactly as expected. Let's see. Yeah, so we don't have problem here in this case, but often we get the problem. We don't require the excess error. We need not compute the excess error. So our error, whichever we computed, so the fit values is actually the true error. We need to again amend this error through other couple of calculations. So our time saved. So the fit value is 0.32 and the error is 0.57. When we add these two terms, and it should be equal to 0.9, and the second value, so the actual values are recalculated from the regression values as well as from the error, and we have, so this is actually what we are searching for. So we already finished our significance test for both beta naught and beta 1 here. I prepared a table which we can use straight away for the reports, but I'm trying to explain. You can export this table as it is. Say for example, if you are writing a report, you can just copy and go to the you can just copy here table 1. You can say that regression output from our regression coefficients from coefficients or regression estimates, whatever, maybe it doesn't matter. Like, okay, we got the table, and you can just start writing it. I think I had to make it anchor. So you can start writing it. The above table is the output for regression analysis in LibreOffice Calc, and you can start criticizing the estimates along with their associated error and the t-value as well as the p-value. As I have explained in my previous video, the beta naught is significant because the p-value is less than 0.05. So at 5% confidence level, as a significance level, we are going to reject the null hypothesis that it is as expected. So it is not the expected value. So there's a lot of difference from the sample statistic may not be a true effect, which we cannot infer. We cannot imply that information to the population, but whereas in the beta 1, which is the slope, is as expected, it can be a true value for the population. So you can start writing like this, and we can also make a couple of graphs for the regression part that I'll show you later. Now I'm trying to explain you how to do the significant test for error. So here we have the error here, and we can go for the sum of the error. We have to take the square, isn't it? So the formula says that that we have to take the square. So the squared error, this is actually EI square by the standard the variance of the y value. Okay, it is variance of the y value, I mean y variable, dependent variable. So we'll compute this. We don't require this because our calculations are 2 here. E square so is equal to square of this value. So Control C, you just have to paste the rest of the cells, and here if we find the sum of the values. LibreOffice Calc has so many wonderful functions for statistical analysis, so we need to worry about these the functions. So here we go for the chi-square statistic. I am going to put this special symbol for chi-square statistic here in this cell. I am searching for the symbol chi. Where is chi? Yes, chi-square. So this is actually chi-square calculated. This is, we are going to calculate a value. So this is calculated is equal to 1 by the variance of y multiplied sum of sigma EI square. So this is actually the the value that we are searching for. We got the chi-square value. Now control, and this is going to be the theoretical value, which we call critical value. Critical is going to be chi inverse at 5% significance level, degrees of freedom. I have 20 data points. 20 minus 1, 19 is going to be my 30. So the case is clear now. The calculated value is less than the critical value, and we are actually going to accept the null hypothesis that the actual the error in the population is 0. So we need not worry, though it is not 0 here in the sample, but the same value will not appear in the population. The actual error, the sum of squared error in the population, is going to be 0. So we are accepting the null hypothesis, and let us check our inference, cross-check our inference with the help of p-value. We have a wonderful function chi distribution, the calculated chi-square value and the degrees of freedom. So p-value is 0.56. Yes, our inference is correct. So we are actually accepting the null hypothesis. If this is less than 0.05, then accept alternative hypothesis, else accept null hypothesis. Yes, we are accepting the null hypothesis because the p-value is greater than 0.05 at 5% significance level. We do infer that though we have some certain effect in the sample for sum of squared error, but the same effect may not appear in the population. The actual error in the population might be 0. Okay, we have a good regression fit through our sample. Thank you.